Hello and welcome everyone. Today we start on Chapter 10 on conics, parametric equations, and polar coordinates. In 10.1, however, we'll be dealing mainly with conics and calculus. So just a quick little mini review. You'll get to see some of my lovely pieces of artwork for the conic sections. Conic section is the intersection of a plane and a double napped cone. So basically picture two ice cream cones glued together. If we insert a plane sort of horizontally this way, we form a circle. If we put it at an angle instead, we will form an ellipse instead. I'm pretty sure you're quickly figuring out why I teach math and not art. If we put our plane sort of parallel to one of the cones, this will form a parabola. And if we put it straight up and down, we form a hyperbola. If the plane intersects the vertex of the cones, we have what we call degenerate conics. If we go just straight through that point and don't touch it anywhere else, we just form a point. If we put the plane exactly on one of the lines connecting them and through the point, make a line. And it is possible if we put it through this way, we basically have two intersecting lines, but those are, again, degenerate conics. We won't spend much time with those. In general, for a second degree equation, we have a conic section. So general. We'd have ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Not the easiest way to graph them, but this is sort of a general that will give us any of those four shapes. The easiest way to define is to use a locus, a collection of points using some geometric property. For example, the most basic of them that we learned the earliest is the circle. Circle is just a collection of points a fixed distance from a fixed point. So the fixed distance is the radius, fixed point is the center. And for those, we can just use the basic distance formula. If the center is at point h comma k, and we take an arbitrary point on the circle xy, The distance, again, we'll call the radius. And we can just use our Pythagorean theorem on there and just make a nice little right triangle out of that guy. So this leg would be y minus k. This leg would be x minus h. And leg squared plus leg squared is hypotenuse squared. Again, that one, pretty sure you've seen that many, many times by this point in your math careers. Parabola, you've played with them quite a bit. They may define it a little bit differently than in maybe your college algebra course, though. Parabola is a set of points that are equidistant from a line called the directrix and a fixed point, the focus. Not on the line. The midpoint of the directrix and focus is the vertex. The line connecting the focus and the vertex is the axis. Okay, parabolas, as you know, can either open up down or left right. Without loss of generality, we'll consider a parabola opening up centered on the origin. So here's our origin, here's our parabola. Lovely, lovely sketch there. So this will be our directrix. And we'll call P the distance between the vertex and the focus, or the distance between the vertex and the directrix. And again, some arbitrary point on the curve that we'll call xy. All right. So again, the sketch, a little on the rough side, but I can sort of translate what we have here. So parabola is a set of points that are equidistant from a line, the directrix, and a fixed point, the focus. So again, as you can see on my sketch, maybe not quite 100% accurate, not drawn exactly to scale, since I'm sketching in freehand and I'm not too sharp of an artist to start with. But each point on here is equidistant from these two places, so distance 1 and distance 2 are equal to one another. So distance 1 equal to distance 2, Distance number 1, again, we can think of our nice little right triangle in there. So distance 1 squared would be change in x minus 0, so x squared, change in y minus p squared. So then distance 1, square root of x squared plus y minus p quantity squared. And distance 2, the shortest way to get to this line is to just draw a nice, neat, pretty perpendicular. So this point here is at x comma opposite of p. So our distance here is just y plus p. Y minus p is y plus p. So then we can say square root of x squared plus y minus p quantity squared is worth y plus p. If I want to get rid of the square root, I can square both sides. So x squared plus y minus p quantity squared is worth y plus p quantity squared. So then x squared is y plus p squared minus y minus p squared. And notice here, this is a difference of perfect squares. I'm out of real estate here, so let me go ahead and flip pages real quick. All right. So then we just do a difference of perfect squares. So y plus p plus y minus p by y plus p minus y minus p. So a squared minus b squared is a plus b by a minus b. Same as a squared minus b squared. A little bit of simplifying in there. We have y plus y 2y. We have plus p and minus p. Those will drop out. This other guy, y minus y, drops out. And p plus p is 2p. The minus p turns it into a plus p. So x squared is 4py. So this would be the sort of general setup. If we'd like to move that around, we can shift left and right, up and down, using work within the with the x and y, the same shifting that you've been doing since your Algebra 2 days. So we could also say x minus h squared. So if we move h units, is worth 4p times y minus k. So this is if we want the center on the generic hk instead of 0, 0. We use 0, 0 just to make our calculations easier, and then shift what happens with that. So this is if we have a vertical axis of symmetry, switch your x's and y's if you have a horizontal axis of symmetry. So if we're opening, you may also remember this as LOS, AOS or LOS, axis of symmetry. Some instructors call it line of symmetry. If we have a horizontal, then we would say y minus k squared is 4p by x minus h. So instead of opening up or down, this one would open left or right. All right, so just a couple quick examples. Focus and directrix. So do y is 3x squared plus 12x plus 7. So we'd like it to look more like these, so we will definitely be completing the square. Hopefully you remember we want a leading coefficient of 1 if we're completing the square. So go ahead and factor that 3 from the first two terms, and we'll just kind of move that 7 over. So then I'm doing half of 4 is 2, 2 squared is 4. I'm writing a plus 4. Don't forget that that's really worth a plus 12. So I'll also have a minus 12 out there. That way we've added 0. So then we have y is 3 by x plus 2 quantity squared minus 5. And if we're looking just to sketch the graph, that would be sort of good enough to sketch the graph. Opens up, vertex at -2, -5, and or vertically stretched by a factor of 3. However, that doesn't help us with finding a focus and a directrix. So for that, I'm going to get the x minus h squared by itself. So I'll add 5 to both sides and divide both sides by 3. So y plus 5 all over 3 is worth x plus 2 quantity squared. So then I'm looking to have this 4 involved, and I don't have a 4 just yet. I have a 1/3. Well, 1/3 is the same as 4 times 1/12. So again, we're going for this format: 4 times p times y minus k on one side, x minus h squared on the other side. So here we can see p is worth 1/12. Vertex is sitting at -2, -5. Since we have the x as the squared one, this is one that's opening up and down. +3 says it's opening up. So again, just a quick rough sketch, and that'll help talk a little bit about the focus and the directrix as well. So here's our vertex in Q3, -2, -5. So we're moving basically up and down by p from there. So if I move down 1/12 of a unit, so -5 is -60 over 12, and we'll subtract another 1 over 12, so that's -61 over 12. And that is our directrix. And if we move up p units from that vertex, so -60 twelfths plus 1/12 is -51 twelfths. The x coordinate was unchanged. So our focus then is at still -2 for the x, but -59 twelfths for the y. So all of the points on this parabola are an equidistant from this line and the focus. So there's our, they didn't ask us to complete a sketch, but there's a nice, pretty little, quick, dirty sketch of what we have. There's one nice, neat property we have of parabolas, and that is the reflective property. So point P, so not P as in the distance between the focus and the vertex, but P for point this time. Some arbitrary xy is a point on the parabola. Then the tangent line at P makes equal angles with two things. The line connecting P and the focus. And the line through P parallel to the axis of symmetry. Again, you may also know that as line of symmetry. So another one of my famous beautiful, beautiful works of art here. So here's our focus. Any point on this curve the tangent line makes equal angles with line parallel to the axis and the line connecting our point and the focus. So in other words, this angle and this angle are equal to one another. And this is why satellite dishes are parabolic in shape. It's that basically any of the information being sent down from the satellite is going to bounce off of the parabola and go through one spot. So that's where they put the receiver. They don't just sort of arbitrarily place it. They do the math and find the actual focus of a satellite dish. All right, so next up we play with ellipses. Definition is kind of similar to how we made a circle, except instead of a fixed distance from a single point, now each is a fixed sum of distances from two fixed points. Now, if you want to sort of see a quick, very high-tech, as you can see, representation of what we're talking about, here is fixed point number 1. Yeah, we'll need some slack there. That much should be good enough for camera work. Here is fixed point number 2. So the sum of the two distances, distance 1, this little nub here, plus distance 2, distance 1 plus distance 2, distance 1 plus distance 2, etc. So there's our super high-tech sketch of the idea of an ellipse. Basically, these two are always going to be a fixed sum. All right, so we'll do a little derivation with that one as well. So we basically have kind of two centers. So distance 1 plus distance 2 is some constant. So again, to make the derivation, we're going to make some simplifying assumptions and then just talk about shifting it around. So we will center this on the origin again. Foci here we'll make at C0 minus C0. And minus A0, A0, points on the ellipse on the x-axis. All right, so a little bit more detail then. So here is our origin. So here's C0 minus C0. A0 minus A0. So remember, distance 1 plus distance 2 is worth some constant. So distance 1, I'm just going to put it above the axis a little bit, plus distance 2. So remember, the string is pinned to the foci. So distance 1 plus distance 2 on there. So in blue we have A plus C. In red we have A minus C. So that will simplify to 2A. So now we're going to move the string to another position. I'll make a sort of a fresh sketch here. So we still have our C0, we still have our minus C0. Only now we have point XY that's on the ellipse somewhere. Well, again, distance 1 plus distance 2 has to be the same constant as before. So distance 1, picture the blue triangle. So we go from minus C to X, so that's X plus C. The vertical distance, the other leg of the blue triangle from Y to 0 is Y. Distance 2, the red distance. Again, another little triangle. So X minus C squared plus Y squared for that one. So distance 1 plus distance 2 is worth 2A. It's also worth the sum of these two. So we'll just set them equal to each other. So 2A is equal to square root of X minus C squared plus Y squared plus square root of X minus C squared plus, my apologies, plus C squared on that one, minus C squared on that one. Okay, so we basically isolate one radical and square both sides. So I don't know, arbitrarily I'll move this guy. So 2a minus square root of x minus c squared plus y squared is worth square root of x plus c squared plus y squared. Square both sides. So we have then 4a squared minus 2a times the square root minus another 2a times that square root, so minus 4a times the square root of x minus c squared plus y squared. And then minus that square root times minus that square root is plus just the argument. So we square the left side, we square the right side as well. And immediately we get to do a little bit of canceling there. I see plus y squared and a plus y squared there. Let's see, we have, and all right, so then we'll get this other radical by itself. Or actually, we can do a little work. We can boil this out a little bit more and get rid of some more stuff. So we'll hang on to the 4a squared minus 4a root x minus c squared plus y squared. Plus, and then I'll go ahead and FOIL this guy out. So x squared minus 2cx plus c squared is worth x squared plus 2cx plus c squared, and we'll get a little bit more canceling done. So x squared, c squared. We can get a little bit more done there. So now we'll go ahead and move the other terms out of the way. So let's see what we have left. We'll clean it up real quick before we flip to the next page. So we'll add 2cx to both sides, and we'll subtract 4a squared on both sides. So negative 4a square root of x minus c squared plus y squared is worth 4cx minus 4a squared. We can even divide both sides through by 4. That out before it makes my writing even worse. Okay, so factoring our friend the negative 4 there. There we go. Factoring the 4, we'll have minus a square root of x minus c squared plus y squared